Hey everybody, today we're going to talk about electron configuration, which essentially means how electrons are configured around a nucleus, because they can actually be configured in different shapes. There's the S shape right here, that's just a sphere. There's the P shape, the D shape, and then the F shape. We're primarily going to focus on these three and how our periodic table relates to these three shapes. So you're going to want to take all of your notes on your periodic table today, and we're going to start off by labeling the different sections of the periodic table for the purposes of electron configuration. So we'll start over here, and our first two groups right here are going to fall in under the S electron configuration. Then we'll jump over here to the right, and groups 13 through 18 will fall under the P category. Now, as I do that, one quick thing that we need to shift, and you can actually do it on your periodic table, go ahead and cross off helium right here and move it on your periodic table to here. Put He right there, because He, helium, fits in more over here, and it is going to be part of the S orbitals and not part of the P orbitals. So that's something we want to clarify right away. Bless me. Now we will look over here to the D orbitals. And all of our transition metals found here in the center, groups 3 through 12, these are all going to be part of the D orbital. So we're just going to focus on those three orbitals right now. We have S in red, D in blue, and P in green. And so what this allows us to do is label our electrons in a different way while also knowing what shape those electrons are actually forming in the electron cloud. So the other thing you need to pay attention to is both the row that it is found in within the columns, and then also the group number that it is located in. So like the rows are going to stay the same: row 1, row 2, row 3, row 4, row 5, etc. And that's going to represent one of the numbers we write in its electron configuration. But the other thing we need to add to our periodic table is within each of the S, D, and P groups, there are specific numbered columns. So let me change that to black. So within S, there is column 1 right here and column 2 right here. So this column is all S group 1. This is all S2. Then within P, there is P1, P2, that's a 2, P3, P4, P5, and P6. And then within D, there is, get that black marker, there is the same thing. We go in order: D1, D2, D3, D4, D5, D6. You can go ahead of me if you want. D7, D8, D9, and D10 right there. All found within the D orbitals. So this would be S1, hydrogen would be S1, helium would be S2, boron would be P1, P2, P3, etc., etc. Now, like I said, the other thing you need to pay attention to is the row. So these are in row 1, row 2, row 3, row 4, and that is all the information you will need to write the electron configuration. Now, we'll start off with hydrogen. So the first thing you write for an electron configuration is whatever row it's found in. So in this case, 1, because this is in row 1. Then you will write whatever group it is found, or whatever orbital it is found in. So hydrogen, you'd write row 1 and then S, because it is one of the S. It is one of the S orbitals right here. And then you put whatever orbital group number it's found in. So you have 1, then S, and then it is in group 1. So hydrogen would be 1s1. Got me? Good. So that is hydrogen. Let's do helium. Helium, again, the first thing you do is you write the row number. So for helium, we would again write 1. Then you write the orbital. It's part of S. And then you write the group number within that orbital, and it is 2. Just like that. Perfect. So helium would be 1s2, and that would be its electron configuration. What that means is it's in the group 1s, and it's going to contain 2 electrons. So that is 1s2. So that is helium. Now, the only place it gets a little bit more complex is if we get over to the p orbitals, which remember start right here in row 2. when we get over to the p orbitals, you actually have to write everything that comes before the different p orbitals. For example, let's look at beryllium. Beryllium, if we just looked at what we just did with helium, we would say it's in row 2, so we would write a 2, right? It's in the s orbital, so we would write an s, and then it is in group 2, so we would write a 2. So it would be 2s2 right there, beryllium. However, with electron configuration, you actually also have to write all of the orbitals that come before 2s2, that come before whichever element you are ending with. Just like in Bohr models, before you could move on to the third energy level, you had to fill up energy level 1 and energy level 2. Well, here, before you can move on to the next orbital, you have to fill up all of the orbitals that come before it. So in this situation, we ended with 2s2. So that means before we could have gotten to 2s2, we would have had to fill up the 1s shell. And we would have had to fill that up with 1s2, just like that. So it would be 1s2, 2s2 for beryllium. Now you're wondering, how am I going to know if each orbital is full or not? Well, each s orbital can hold 2 electrons. So each s orbital can hold 2 electrons. So you can do 1s2, 2s2, 3s2, 4s2, etc. So all s orbitals can hold 2 electrons. We come over here to p, and all p orbitals, we count up to 6. So all p orbitals, draw an arrow right here, all p orbitals can hold 6 electrons. So you know a p orbital is full as soon as it has 6 electrons. You know an s orbital is full as soon as it has 10 electrons. And d orbitals, you know d orbitals are full as soon as they have 10 electrons. So that is how we will know when something is full, is if s has 2 electrons, if d has 10, and if p has 6. Now, before we go forward anymore, I'm going to show you this wonderful diagonal arrow diagram that you also have a copy of. What this does is it actually shows you the order that you need to go whenever you're filling in these different electron energy levels. So you start here, you move down the diagonal arrows in the order from top to bottom, so here, 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 and they will give you the correct sublevels for electrons every single time. So we always start with 1s, then go to 2s, then 2p, then 3s, then 3p, then 4s, then 3d, 4p, 5s. We're not going to get that complicated just yet. We're just going to stick with s and p. So I'm going to do one more example, or 2 more examples in this video. Let's do an example with boron right here. Boron. Okay, we're going to start off by just writing its simple electron configuration, and we're going to do that by looking at the row that it's in first. Remember, it is in row 2. So we are going to put a 2 right there. With me so far? It is in the p subshell, so we are going to write a p right there. And then it is in group 1 within the p subshell, so I'm going to write a 1 right there. Okay, that part we have down, right? Now, what do we need to put before that? Because remember, you have to write everything that came before it. Well, that is where this handy-dandy diagonal diagram comes in. We just determined that boron is 2p1, so we go here and we find 2p. 2p is right here. All we have to do is put each energy level that came before it. So 2p is right here, so the only energy levels that came before 2p were 2s and 1s. So all we have to write before this is 2s and 1s, just like that. And then, as I mentioned just a moment ago, those both have to be full before we could have moved to 2p. And in order for those to be full, they needed 2 electrons. So we have to write 1s, and we just have to add a 2 right there. And then we have to add a 2 right there. So we have 1s2, 2s2, and then our boron, its actual electron configuration is 2p1, just like that. So one way you can check your work too is these little electrons on top, 2, 4, 5, should all add up to equal the atomic number. And you see that boron's atomic number is 5. Okay, we'll do one more example. Last one. Okay, let's look at sulfur right here. This is a longer one, so let's look at sulfur. Okay, with sulfur, let me erase this here. With sulfur, let's write its electron configuration first. It is in row 1, 2, 3. So the first thing you write, 3. It is in the P subshell. So we write P, 3P. And then we see which column it is in or which group it is in within the P subshell. It is in group 1, 2, 3, 4. So 3P4 is where we're going to end up for sulfur. But remember, we have to write everything that came before 3P4. So we look at our diagonal diagram. 3P is right here. Let me erase where we circled 2P. Okay, 3P right there. So we have to write everything that came before 3P. So let's look at what came before 3P. We have 3S, 2P, 2S, and 1S. So that's what we have to write in reverse order. So we go 3S, then 2P, then 2S, then 1S. So we go 3S here, 2P here, 2S here, and then 1S. And then the last thing we need to do is we just make sure all of these orbitals are full. So for all the S's, we just put 2's, 2, 2, and 2. And for all the P's, remember, we put 6, 6 right there. And now we can check our work, make sure it all adds up to 16. 2 plus 2 is 4, plus 10, sorry, plus 6 is 10, plus 2 is 12, plus 4 is 16. So that equals the atomic number right there. So that is how you do electron configuration for the S and P orbitals. So practice that. We'll get the hang of it. It's a very quick introduction to electron configuration. Make sure you have everything on your periodic table labeled, and we will do some practice problems. Good luck. Farewell.